بسم الله الرحمن الرحيم. السلام عليكم، ازيك يا شباب، عاملين ايه؟ النهارده هشرح chapter 3 اللي هو عبارة عن Fourier series، وهيكون آخري لحد ال rectangular pulse signal expressed in complex exponential Fourier series. فتعالى أولا نعرف ايه هي أصلا Fourier series. ويعتبر هي mathematical tool used to represent periodic functions as a sum of simpler يا sinusoidal components or complex exponential components، على حسب انت هتستخدم أي نوع ايه بالظبط من Fourier series عشان فيه اتنين. فاللي احنا هنتعامل معاه النهارده هو ال complex exponential. So if you have any periodic signal, it can be rewritten as مثلا if you have a signal g of t, we can rewrite it as the summation or the sum of the signal is known as the summation of dk times e to the power of j k omega naught t, and dk is our Fourier coefficient. and أو عشان أصلا نجيب الفورير سيريز في الشكل اكسبوننشال احنا في الأول المفروض نجيب الفورير coefficients. ف dk can be found by 1 over t naught, the fundamental time period in which it repeats itself, time multiplied by the integral of 0 till t naught, or basically written like this: the signal itself multiplied by e to the power of negative j k omega naught t dt. So these are the formulas you need to find the Fourier series of a periodic signal, while also keeping in mind that this is how we calculate the Fourier coefficients. هو في شوية حاجات أو في مثلا شوية properties أو خصائص للفورير سيريز. إن أولا أصلا the Fourier coefficient at 0 is basically the average value of the signal, or it's also known as the DC component of the signal. So at d equals 0, that's the DC component of the signal. Also, dk itself will be real as long as the signal we have is even, which can be written by this form. And also, or let me write and, dk or the Fourier coefficient will be imaginary if gt or the signal we have is odd, which is also written like this. So one example we have is the cosine terms. So if we have cosine, cosine is either even, I'm gonna write this just even, and here is odd. I had to change the mic. So an example of this is if we have cosine, which is an even signal, if we rewrite it into its exponential form, we'll have 1 over 2 or half times e to the power of ix plus e to the power of negative ix. This is basically the Fourier coefficient, and these are the sum of the complex exponentials which describe what we have here. So now we could actually just say that the exponential form of the cosine is basically its Fourier series. And similarly, if we also reiterate back to the same point we had here, to prove that the Fourier coefficient for an odd signal will be imaginary, if we look at sin x, we'll know that its exponential form is basically 1 over 2i, and the one, sorry, not they're not added, they're subtracted from one another. Yeah. So this is the basically the Fourier series for sine when written in exponential terms. And as I said, the Fourier coefficient when the signal we're dealing with is odd in nature, your Fourier coefficient will be imaginary. Next is also something related to Fourier series, and it has to do with the conjugate of the Fourier coefficient. I'll not go down to proving it. I'll just say that the magnitude of dk is also equal to the magnitude of the Fourier coefficient at negative k. That's all you need to know. And an extension of this point or of this property is that dk is equal to 0 when k is even for an odd signal, which is basically this. Now let me re-explain it. That the Fourier coefficient at an order basically of k which is even will equal to 0 as long as the signal you're dealing with is odd in nature. And I think so these are all the properties that we need to know to continue solving. And one last thing is يعني عشان ما اكذبش عليكم وافوت معلومه ان في حاجه اسمها الاورثوجوناليتي. this is O A L I T Y yeah. اللي هو مثلا لو انت عندك 2 signals ضربة في بعض basically the product of the dot product will basically equal to 0. فلو اتكلمنا على الاكسبوننشال if we have e to the power j omega node t times e to the power negative j n omega node t dt. This could either have two values, equal to 0 if m doesn't equal n, I mean, and this basically means that they're orthogonal. However, if they're equal, then all these will just cancel out and be e to the power of 0, which is basically t, and we're already integrating along an interval of this, which is basically going to equal t naught, as long as m is equal to n. And let's move on. Let's now solve an example with what we've just mentioned. We now know what the Fourier series looks like, and we could also find the Fourier coefficients. So now we have a question. It's asking us to find the Fourier series of this exponential signal e to the power negative t over 2 when the fundamental time period in which it repeats itself is pi. So first of all, let's just write down the formulas that we know. We know that any periodic signal is equal to the summation till infinity, and starting from k equals negative infinity, the Fourier coefficient times the complex exponential term jk omega node t. And we're already given what omega node will technically look like indirectly. We know that omega node is equal to 2 pi over t node. So you just replace t node with pi, 2 pi over pi cancels out. So you have omega node equals 2. So now you can just replace this omega node with 2. And also, let's find, first we need to find the Fourier coefficients in order to calculate our Fourier series, and it's going to be given by 1 over pi, 1 over t naught basically, across an integral of from 0 to pi, the signal itself negative t over 2 times e to the power negative j k omega naught, which is 2t dt. And let's calculate this integral that we have here. So we could combine the exponential terms with each other or their powers. So let's do this. 1 over pi integral from 0 to pi of e to the power negative. I can just take the negative as a common factor. And also, since I'm already dealing with a variable of t, so I'll also take the t as common. So I'll be left with 1 over 2 in the first signal, and the second signal I'll be left with this, which is jk2, so plus j, and let's just write it in this form, and it's all multiplied by t, integrating with respect to dt. So if we were to integrate this, obviously any integration of an exponential term will basically be equal to over ax over a. Whatever is beside the x will be divided by. So now if we were to go back to our integral, what we'll have beside the t, which is the variable that we're integrating with respect to, we have all this mess. Okay, sorry, I kind of made a mistake in my previous recording. It's just, I made a mistake in the sign. So I have to now repeat. So yeah, this is where we stopped, and we could just take the integral of this as the whole exponential term divided by what's next to the t, which is this. So let's do that. we have 1 over pi, and then we just open the bracket. We have negative 1 over 2 plus j 2k over e to the power of negative 1 over 2 plus j 2k t across a boundary from pi to 0. And what I could do is I could also just take this bracket out. So I'll be left with 1 over negative 1 over 2 plus g2k over 1, and I'll just be left with the exponential. Or multiplied by t over a boundary of pi to 0. And now let's just replace each term. Then minus 1, because either way, if you replace the whole exponential or the t as 0 in the whole exponential term, to be e power of 0 equals just 1. So it doesn't matter. And now that's what we have here. And let's simplify this exponential term we have here. Let me take it as a different color and rewrite it. You can just write that negative pi over 2 times e power of negative j k 2 pi, right? Yeah. And you could rewrite this as, because e power of ix is equal to cosine x plus minus I sine x. So if we use the same concept to simplify this term we have here, we'll be left with e to the power of negative j k 2 pi. That's equal to cosine k 2 pi minus j sine k 2 pi. Any constant I multiply by 2 pi in cosine is basically 1, and sine 2 pi of any sort, even if there's a number multiply next to it, is going to be 0. So now I could just rewrite this as 1 minus 0. And don't forget the negative pi over 2 here, my bad. Either way, this term is gone, so it's just basically I have this and this. Now let's rewrite everything. We have negative 1 over pi 1 over 2 plus j 2k multiplied by what's it? E negative pi over 2 minus 1. If we were to input this in the calculator, and what we'll do is calculate this part multiplied by this part, and we'll just be left with the complex denominator, and that will be equal to 0.252 all over 1 over 2 plus j 2k. And we could simplify this even further by multiplying by 2 in the all over the entire fraction. We'll be left with 0.504 over 1 plus j 4k. Am I right? Yeah, so this is now your dk. This is the simplest form of the Fourier coefficient that you found after integrating it. And now this should just put this back in our Fourier series formula. So we have summation starting from k equals negative infinity. You have 0.504 over 1 plus j 4k multiplied by e power of not negative j k 2t, yeah, 2t. And all you have to do now is just start with k equals 0, and then you move on with plus minus 1, plus minus 2, and so on. So now let's calculate what the Fourier series will look like when we start with k equals 0. So at k equals 0, we'll replace each k with 0. So we'll be left with 0.504 over 1 plus 0 multiplied by e to the power of 0, which is basically 1. So all of that will be equal to 0.504. And this is basically our DC component. Let's now find the Fourier coefficient at 1. And this will be equal to 0.504 over 1 plus 4, right? G4, yeah. E to the power of J2T. And now what do we have here? We have basically the term of the Fourier series at k equals 1. We have here the Fourier coefficient multiplied by the complex exponential term, which is basically just another form of this. So now let's calculate the magnitude of this Fourier coefficient such that we could rewrite it into our Fourier series. So if we want to find this what's called d1, what we're going to do is going to multiply by the conjugate to get rid of this complex denominator. So all we'll do is 0.504 multiplied by 1 minus j4 over, I have 1 minus, and then these basically 4 times root negative 1 all squared. This will be basically 4 squared times negative 1 squared. This will be 16. This will be negative 1. Negative 1 will go outside, cancel it out. So in the end, what we have here is, what the hell? Nah, give me a minute, bro. Yeah, so after all of that, we'll have 1 plus 16, which is basically equal to 0.504. And then let's just expand the bracket. 0.504 times negative 4, that's basically going to be 2.016J, all divided by 17. And the way we could calculate the magnitude of this term now is by taking the real part and squaring it, and adding also the magnitude of this imaginary part and squaring it as well. So what I mean by this is now the magnitude will basically be equal to 0.504 over 17 all squared. I'll just write it like this, plus negative 2.016 over 17 all squared. And if we were to write this in the calculator, and yeah, apologies, I'm actually calculating it. We're going to have 0.122. So this is for D1. So now, if we were to rewrite the term of the Fourier series at k equals 1, this will be equal to 0.122 e to the power of j 2t. And you could continue on with this different terms at what, plus minus 2, plus minus 3, and so on. And either way, this will also be equal to, subsequently, if we find the conjugate to find d at negative 1, this will be equal to 0.122 e to the power negative j 2t, if I'm not mistaken. Yeah, so this is how we found the Fourier series. And I'm not going to continue along with the same steps، مش هي نفس الخطوات هي وكمان في نفس الوقت احنا عرفنا ازاي نجيب الفورير coefficient باستخدام الفورمولا بتاعتها. Before I go on and explain another topic, let me just clarify something, that the Fourier series itself is linear such that if we have a signal which is constituted of other signals، احنا عندنا signal وهي عبارة أصلا عن على signals تانية، فمثلا عندنا x1 of t بيساوي or my bad. If we have a signal of x of t is equal to x a sum of signals plus x2 of t. وتعالى مثلا نقول إن ده مثلا A it has a amplitude scaling factor of A and here is B. So if we were to find the Fourier coefficients, basically this would be equal to itself basically, but in Fourier form or the coefficient form. A dk1 plus B dk2 to find the Fourier coefficient of the signal as a whole if we already know these two signals. And let's solve another question on Fourier series. So we're given a signal of f of t is equal to 3 plus 4 cosine omega naught t plus 2 cosine 2 omega naught t. And we're asked to find the Fourier coefficients. أولا لما نبص على السيجنال كل حاجة linear. بمعنى إيه؟ بمعنى السيجنال معاك لوحدها it's not multiplied by itself, it's not multiplied to any other signal, it's by itself. All you have is cosine, and also here all you have cosine with طبعا an amplitude scaling factor. فلو احنا بصينا الفورير سيريز بشكل تاني، لو بصينا على التريجونومتريك فورم ده يعتبر اصلا ده السيجنال ده عبارة عن فورير سيريز. يعني اصلا the Fourier series of a trigonometric form انا بس اكتبها على كام كده هو يكون a naught plus summation k equals negative infinity or n, it doesn't matter يعني. You have an cosine k omega naught t plus bn sine k omega naught t. So these are your Fourier a and bn are your Fourier coefficients for the combination of cosine and sine terms. ولكن احنا بنتعامل مع الكومبلكس اكسبوننشال، فتعال نغير كل كوزاين ايوه كل كوزاين ونخليها في الشكل الاكسبوننشال. وكده كده زي ما اتفقت من الاول اصلا ان الاكسبوننشال فورم بتاعت الكوزاين يعتبر هي الفورير سيريز بتاعتها. ولكن تعال نعيد النقطة تاني عشان نفهم اكتر. ف we have 4 بعدين open a bracket and rewrite it in exponential form. We have e to power omega no g omega naught t plus e to power negative j omega naught t all over 2, and the second signal also the same thing as well, e to the power of j 2 omega naught t plus e to the power of negative j 2 omega naught t على 2. And if we just simplify even further, this will cancel out, this will be left with 2, and these will just cancel out and be left with 1. And زي ما اتفقت ان الرقم اللي جنب sum of exponential terms في الكوزاين هي راحت فين؟ يعتبر هي اصلا ال dk، ده يعتبر الفورير كوفيشنت. فلو بصينا دلوقتي على الشكل ده احنا عارفين دلوقتي ان الفورير كوفيشنت so now we know that the Fourier coefficient for at d at positive and negative omega naught t على حسب الدومين اللي انت هتتعامل معاه. مثلا لو اوميجا نود هيكون ب1، او مثلا if it's t then it be omega naught whatever it may be is equal to 2. As I mentioned, the scaling factor which is next or multiplied to the sum of exponential terms which is the equivalent of cosine is the Fourier coefficient. And same thing, so this is at positive and omega positive and negative omega, and for the second cosine this would be at positive negative 2 omega naught t is going to be equal to 1, as these will just cancel out, and at 0 d0 equals 3, which is the dc component. Now let's jump to a new concept called Parseval theorem, or it has to do with the power spectrum density, PSD, power spectral density. And if we go back to the formula of the power of a periodic signal, it will be basically 1 over t, or 1 over t naught, and its integral from 0 till t naught, it's magnitude squared. So we have dt. And what Percival's theorem states that the power of a signal is also equal to the sum of the Fourier coefficients, and squared, like this. So this is Percival's theorem, and we'll need this theorem to understand what the power spectral density itself is. And it's basically a distribution of the power of a signal across different, or across a specific harmonic or frequency components. So an example which is already mentioned in the slide here is it's like this. And we have omega naught here, or it could be also denoted as f, it doesn't matter, but let's just stick with omega for now. And here are different, express this like distribution of density. We're going to state it right now. It's 2 pi times dk all squared, and then the summation, let me just erase this. The summation at negative infinity, and starting from negative infinity, and just the unit impulse omega minus k omega naught. So and بص انا عارف ان في كلام كتير، مثلا المعيدة نفسها بتقول ان مفيش مثلا السبمشن او مفيش 2 باي، او حتى في السلايد مش كاتب اصلا الحتة دي او الحتة دي. فخليني اكد عليكم على الكلام ده عشان أنا صراحة it's not like I know any better. So yeah, this is what I'm going to deal with for now. فتعال نتكلم على اخر حاجة. نسيت اقول لك برضو حاجة، ان if we use this definition now to find the power of a signal, and it's basically if we take the summation of this as well, so it's going to be 1 over 2 pi summation s k omega naught. And now let's move on to our last topic, which is the rectangular pulse train, or basically just a sequence of repeating rectangular pulses like this. And let's assume that its pulse width is tau. So we have negative tau over 2 here. We could say this is 0, tau over 2. And we now could also deduct or assume that t naught is basically this interval right here. So we could say just negative tau over 2 t tau over 2. Or this is where it repeats itself across different intervals. And obviously if you take the summation, you're going to have n here and n here, and it will start repeating itself if you write it as a sequence or summation form. But for us to find the Fourier series of this signal, let's first of all define it. We have example g of t is equal to a times, let's say it could be either written as like this or like this, it doesn't matter, t over tau if I'm not mistaken. Or I could also write shift, the shift here, but then the shift will be also have to be a subject of the sequence, and you have to add n. For let's just keep it in its simplest form, and this is what we have here. And if we were to define it across its domain, so it will be equal to a at this domain. As you can see here, I'm only dealing with this part, and anywhere else for now is 0 for otherwise. And let's find the Fourier series of this signal. So first of all, we know that any periodic signal can be rewritten as its combination of complex exponential terms find Fourier series, we first have to calculate the coefficients. So I have 1 over t node, and we have negative tau here and tau here. We have the signal itself, which is defined at a, and you replace this a and just write it here. So we have a over t node, and all we left here is with the exponential term dt. We will not rewrite this, will be a over t node. And we could also know that since the integral will just basically be the exponential term divided by this, I could rewrite it outside. We'll have negative g, or no, wait, let me just write the exponential terms first. Be negative e to the power negative g k omega naught because either ways, so these will cancel out. So you could just decide not to write them. All over g, or my bad, negative g k omega naught. And if I were to distribute this negative 1 into the both terms, I can rewrite it as this will be positive and this will be negative, and you'll see why I'm doing this now. If we go back to what Euler's formula states, if we have sine x equals e to the power of ix minus e to the power of negative ix over 2i, and if we want to find what this sum of exponential terms will be like, we just multiply 2i here as itself, and as a subject. So we have 2i times sine x equals e to the power of ix minus e to the power of negative ix, and kind of have the same picture here. So if we now were to rewrite this, a over t node will be left with 2j sine, and then whatever inside the bracket will have k omega node tau over 2, alright, k omega node tau over 2, yeah, over j k omega node. J's will cancel out, and if we were to also remove each omega and replace it with its equivalent, 2 pi over t node, and let's do that right now. A over t node, we have 2 sine k times 2 pi over t node times tau over 2 all over k times 2 pi. Let me just write the 2 properly, whatever, over t naught. So I know the 2's will cancel out here, 2's will cancel out here, and the t nodes will also cancel out here. So if I were not to rewrite this, I'll be left with a over k pi, and basically the whole denominator is gone. I already took them out here, so I'll be left with sine k pi tau over t naught, and yeah, that's what we have here. So this is basically one of the simplest forms you could reach with the Fourier coefficient for the rectangular pulse. However, what we could do is that we could rewrite it in a different form, in a form like this. It's sine c of x, or cx, I have no idea how you say it, is equal to sine pi x over pi x. And if I were to compare these two, I could assume that whatever I have as pi is also here, and x is just basically these terms. So what I need to do to reach it, to get this here, is I just multiply it up and down here. Whatever is the x, sorry, yeah, I just basically multiplied by this pi x or pi and or this entire term up and down. So if I were to do that, I'll be left with a over k pi times k pi over t, and and I could just rewrite this as sine k pi tau over t, and k pi tau over t naught. I'll be left with, and now that I achieved this form, I can now rewrite everything as a tau over t naught, and rewrite it as the sine c thing, k pi t or pi tau over t. And this is what the rectangular pulse looks like in another form as well. And there's a definition for Boston, something called as the duty cycle. It's just basically a ratio of how long the signal has been activated or on compared to the entire signal period, or basically tau over t node, or tau over t, doesn't matter. But in this case, we're dealing with t node, and it's denoted as d. So for now we're just to rewrite everything. We'll have ad sine c kd, right? And since we write it in this form, then there is no pi written inside. So this is what we're left with. So it will be written as kd. This is also another form. So we basically reached three forms here. We could also rewrite this as a over t naught to sine k pi tau over t over k pi tau over t. And you know why I'm writing this. You could use this form now to find the Fourier coefficients. And this is just basically a simplification of it. So now to find the Fourier coefficients, and for us to do that, we'll have to do some assumptions. For let's assume that a equals 1, and the duty cycle is also half. So at d of 0 is going to be equal to half, or 0.5. And at d1 is going to be equal to 1 over pi. Wait, sorry. Half pi, my bad. Or apologies, no, wait, I was just looking at the calculation wrong. 1 over pi. It's going to be found by 0.5 or half sine 0.5 pi over 0.5 pi. That's if you replace each k with 1, and the duty cycle as half. And this is also equal to -1, by the way. They're the same thing. And at 2 and -2, it's equal to 0. And at d3 and -3, it's equal to -3rd pi, or -1 over 3 pi.